Okay, so free body diagram. We have the 400 Newton force to the left. The cable force is away from the chosen body, so tension that way. There's a weight force of 20 kilograms times 9.81, so 196.2. And then the pin joint has an unknown force vector, so call that FP pin. And okay, so set up the table. The 400 Newton force is acting at negative 0.5, positive 0.02. We're going to use the origin as the about point, so that's zeros. The row vector is negative 0.5, positive 0.02. The force vector is negative 400, 0. And so you should get positive 8. Is that right? And now go to the tension force. The tension force is acting at 0.6, 0.4. About point is 0. So the row vector is 0.6, 0.4. The force vector, the relevant angle here is 45 degrees. So this is going to be 0.7071 t, 0.7071 t. That's just cosine and sine of 45. What do you get with this cross product? 0.142? 141. Oh. T. And then go to the weight force. That's acting at the origin. So the row vector is 0. The force vector is 0, negative 196.2. No moment. And then the last one is the pin joint. That's acting at 0.05, negative 0.2. So the row vector is 0.05, negative 0.2. The force vector is F, P, X, and Y. And so you get 0.2 FPX plus 0.05 FPY. Is that right? Okay. Okay, so Newton's second law says negative 400, 0 plus 0.7071 t, 0.7071 t plus 0, negative 196.2 plus fpx fpy is equal to zeros. And the rotational equation says 8 plus 0.1414t plus 0.2 fpx plus 0.05 fpy is equal to 0. Okay, so now we have to choose an equation, order for these variables. So let's go fpx, fpy, t. And then the constants. So equation 1 is the x component of Newton's second law. We have 1 fpx, 0 fpy, 0.7071 t is equal to positive 400. Equation 2 is the y component, 0 fpx, 1 fpy, 0.7071 t is equal to positive 196.2. And the third equation says 0.2 fpx, 0.05 fpy, 0.1414 t is equal to negative 8. And if you make this matrix, use RREF, what do you get for the answers? Anyone do that yet? 2766. Okay. Oh, okay. Mm-hmm. Okay, and tell me the tension again. 2766. Okay. And do those match what I got in the solution? Hopefully they do. They should. So what if instead of being asked for the cable tension, so the cable tension is a scalar, it's just 2766. What if you were asked for the force vector that the cable applied to the body? How do you get that? Yep, so you could just take this value, plug it back into, this here is the force vector applied to the body by the tension. So plug 2766 in for t, and that would give you the force vector.
But on the exam, we can just leave that as a scalar?
Well, if I ask you for it as a vector, I'd like you to give it as a vector. Yeah. Otherwise, then yeah, that's fine, unless I specify the vector.
When does the rotation matrix come into play?
That will come up.
Oh, we're not using it because you
not
went
yet.
Over it.
Yeah. So
We had like
that came up, I think, when I was talking about friction, but it's not really going to be you're not going to have to use it until we start talking about internal loads of structures. Okay. Any questions about that? Okay, well, let me just start getting into structures with an example problem. Like, really, there's nothing about structures that we're not capable of sort of thinking our way through right now. But I am going to give you a set of steps that'll make it kind of easier to follow. So let me just start by giving an example problem. So let's say that we have 2 bars connected by pin joints and connected to the ground by pin joints. So just so we can refer to these things easily, let's call this member 1, this member 2. Let's call this pin A, this pin B, and this C. And then we need some kind of force on this, otherwise the answer is 0. So let's say that there's a 500 Newton force applied to the right at the pin. And let's say that this angle is 60 degrees. So I guess this whole thing, I made it look a little lopsided, but this is an equilateral triangle. So let's make this length 1 meter. This is 60 degrees. That means that this length is 1 meter and this length is 1 meter. I'll put the origin down here.
What kind of joint is at the top?
A pin. Yep. So all of these joints are pins. And the question is, what are the external forces on each of these members? So the way I'm going to do this is, if you think of a pin joint as, so there's one member over here and another member here. Let's see. This is a terrible drawing. Let me fix this. Okay, so you have one member like this. Okay, and connected to it is another member like this. And the way these are attached is this pin goes through the center of them like this. Okay? So that's a pin joint. And so what I'm going to do at each of these joints is I'm going to break it up into, so I'm going to think of this as 3 separate objects. There's the pin, and then there's member 1 and member 2. We're going to assume that the pin has no width. Okay, that width is pretty small. And so in 2 dimensions, I'm going to think of these pin joints as, so here are my options for choosing what members to look at a pin joint. I can do a rigid body, like say we're looking at the pin at A. I can isolate rigid body 1, and then that pin is applying a force to body 1. Or I can isolate the pin. Instead of treating that as a rigid body, I'm going to treat that as a particle, because we're just going to assume that it has no width. And that particle has a force applied to it by body 1. Okay, so that's the way I'm going to try to come up with enough equations to solve for my variables. So let's just start drawing free body diagrams and writing Newton's laws. And basically, we're just waiting until the number of equations we have catches up with the number of variables we have. Okay, so the first thing I'm going to do is isolate the whole thing. This is not including the pins, but I'm isolating member 1 and member 2 and the pin that attaches them as a single object. So what forces are acting on this object? Yep, that for sure. Well, we're neglecting that, but it would be, yeah. And then the pin at A is applying a force here. What type of force is that pin applying? Unknown vector. So I'll call that the force on member 1 by A, by the pin A. And then over here, same thing. There's a force on member 2 by the pin C. Yeah, we're neglecting that though. Well, okay, so that, we are going to have to deal with that eventually, but that doesn't show up here because that's internal to our boundary. Okay. Okay, so let's set up the table. So first, the force 1A, that's acting at, in this coordinate system, negative 0.50. The about point, let's just make the origin the about point for all of these. So the row vector is negative 0.50. No, let's not do that. Why? Why would we do that? So let's make the about point, make it a little easier for ourselves, and put the about point at A. So negative 0.50. And so subtract those and you get a row vector of 0. The force vector is F1A x and y components. And there's no moment. And now let's go up to the 500 Newton force. What are the coordinates where that force is applied? Square root of 2, I think, right? Yeah. So we have 0, 1.414. The about point is still this. So the row vector is positive 0.5, positive 1.414. The force vector is 500, 0. And so we get negative 707.1 for the moment. You could do this as 2 right triangles. We have a length of 1 here, an angle of 60, so you could do 1 times sine of 60 gives you the height there. And now where this F2C is applied, that's at positive 0.50. Our about point is negative 0.50. Oh yeah, so my origin is just below the top here. So we have 1, 0 for the row vector. And the force vector is F2CX, F2CY. And so the moment is F2CY. So Newton's second law says F1AX, F1AY plus 500, 0 plus F2CX, F2CY is equal to 0. So that gives our first two equations. So I'll write them as F1AX plus F2CX is equal to negative 500. And the second one says F1AY plus F2CY is equal to 0. And then the rotational equation says negative 707.1 plus F2CY is equal to 0. This one we could solve for F2CY, but we're going to end up with so many equations that it's not even worth bothering with that. We'll just call that equation 3. Says F2CY is equal to positive 707.1. Okay, so from the first object that we isolated, we have 3 equations. So let's figure out how many variables we have. So we have 2 variables here, the x and y components, and 2 variables here, the x and y components. So we have 4 of these, F1AX, F1AY, F2CX, and F2CY. Okay, so we're not that far off from being able to solve it, it looks like. We'll see that we are pretty far off. But we can't do anything yet. So we just have to keep moving. And so let me just draw the free body diagram of the next step that we're going to take. And we'll just keep going with this next time. So next, we're going to draw a free body diagram of body 1. I mean, it really doesn't matter what order you go in. So what does this look like? What forces are applied to body 1? Well, we still have this. We still have the force applied to body 1 by pin A. But now we have to think a little more carefully about what's going on at the top here. What about that 500 Newton force? Is that applied to member 1? Well, no, that's applied to the pin itself. So that's not going to appear here. Okay. And let's also, notice how I drew this gap between these 2 members. We're going to assume that these members touch the pin, but they don't touch each other. Okay. So there's no force vector applied to member 1 by member 2. But there is a force vector applied to member 1 by the pin. Okay, so up here there's a force vector applied to member 1 by the pin B. Okay, so that's the next one we're going to do. I guess let me just stop there. We'll keep going with this next time. So, okay, there's a test tomorrow and office hours at the end of the hall right now.